Welcome protein coders. Let's build some coding muscles. Today we're gonna study update query in segment trees. Earlier in our series we have studied about how to build a segment tree. So here let's say we have a vector given, okay? And in segment tree we studied that we use segment tree to perform fast range queries, right? That want to find sum of index 0 to 1 or 0 to 2 or 0 to 3 or 1 to 2, right? Now you may have a question like we can use prefix sum for this also, right? But there is an issue here. What if I have an update query, like I want to update an element in my vector, right? Then I have to change the complete prefix sum after that index, right? And in worst case, let's say I am updating the first element of the vector every time and then performing the array in some queries, then I have to update the complete prefix sum array, right? The time complexity will be very high. Like in worst case, it will be the number of queries times n, where n is the number of elements in our vector, which is very high. So today we will see how we're going to perform the update query in our segment tree. So suppose we have our input vector, which has elements 2, 1, 4, 3, and L and R represents the starting and end index of the vector, and here I is the index of the elements in the segment tree, okay, which is of size approximately 4 times the number of elements in the vector. We studied this earlier, right? How to build a segment tree. Now let's build our segment tree. So the left node will be at index 2i plus 1 in our segment tree, comma L comma mid, right? Mid is nothing but L plus R by 2. For second node, it will be at index 2i plus 2, right? Which is 2 into 0 plus 2, which is 2, right? And mid plus 1, comma R. So in similar fashion, let's build our segment tree, and the value of the node in the segment tree is the sum between the range L to R, okay? So for the first node, it's the complete sum of the array, which is 10, then 3, 7, and finally when we reach the leaf nodes, sorry, it will be 4 comma 1 comma 1, okay? So when we reach the leaf nodes, we will return and fill our segment tree. So we will get the indexes of the segment tree and the value of the nodes, and while going back we will add them and fill them in the segment tree. Now let's suppose I want to change the element at index 1, okay, with value 3 instead of 1. Now how I'm gonna perform this in a segment tree? First I will calculate the mid for the first node, and if the given index idx is less than or equals to the mid, I will move left, or else if the idx is greater than mid, I will move right. And at the end, when I reach a place where L is equals to R is equals to idx, I will change the element, and while returning back I will again perform the similar segment tree operation. I will add the child nodes, right? So now if you calculate the range sum of any, let's say any range 0 to 1, you will get 5. From 0 to 2 it's 12, and it's correct. So here you see we have to perform very few operations. We have to change only 3 elements. We didn't require to change whole segment tree as we are doing in prefix sum. So let's see the code for this. Let's have our void update. Here I, L and R are index of segment tree, L and R are the starting and end index of the vector. First we will find the mid for the root node, and if idx is less than or equals to the mid, we will move left in a segment tree, right? That means the I will be changed to 2i, 2 into I plus 1, right? And L comma mid, we move to the left node of the segment tree, or else we will move towards the right side of the segment tree and call update. And at the end, when we find condition IDX equals to L equals to R, we can directly update the element in a segment tree and return. And while returning, we will update our segment tree as we did in our building segment tree code, right? SGT of I is equals to SGT of sum of 2i plus 1 plus SGT of 2 into I plus 2, sum of the child nodes. We first find the mid. If IDX is less than mid or equals to mid, we will call the recursion and move towards the left node, or else recursively we move to the right node. Right at the end, if we got the condition IDX equals to L equals to R, that we found our element to be changed, we will change it, and while returning we will update our segment tree. Now if you observe in our prefix sum, the time complexity is order of n, right? But here it's just about the height of the tree, which is log of n, where n is the number of nodes in our vector, right? So we improved our time complexity from order of n to order of log of n. So that's all from my side, guys. We have studied about how to build a segment tree, how to update a segment tree. In next videos we will see how to range query in a segment tree. Okay, if you have any questions, please mention them into the comment box. I hope this helps. Keep practicing, keep smiling. Thank you.